Hello, Matsuyama. I'm Daisuke. Today we're going to talk about profile and benchmark every change. Some of you might know me as Oshoyu, since that's my online handle. I work at Smart Bank Inc., which is a credit card company. We're hosting the hack space on the second floor, so please take a visit if you want to hack away or just want to relax. I usually work as a Rails developer at SmartBank. And before we go into the main topic, I'd like to deliver some updates from my own Ruby profile at PS2, which was received 5 honorable mentions as a keynote. I'm sure I don't have to explain what profiler is, so I'm just going to deliver recent updates. I've changed some internals, so reduced memory consumption by 90%, and I have expanded features for comparing profiles, which I'm going to explain later. And I have rewritten the core in C from Rust. And one thing I have realized this year is that profilers don't make programs fast. Just like debuggers don't find bugs, profilers itself don't make the program fast. So today, I'm going to address that. Today, I'm going to speak about 3 things. One is introducing benchmark-driven development, which I will refer as BenchDD. Now, next, I'll show you the toolset for doing BenchDD. And lastly, I'll show how I applied benchmark-driven development to build a 100 times fast version of Sinatra. Also, for this year, I have attached a short Japanese translation on the slides as an experiment. This part is pure translation, and it doesn't contain any flavor text. So if you don't read Japanese, you can safely ignore it. I have created a web framework called Sinatra. It implements a fair part of the Sinatra API, so it can be used as a drop-in replacement for Sinatra. You can simply change your app's base class from Sinatra base to Sinatra base. I first thought to name it Sinatra, since C is 100 in Roman numerals, but I soon realized that it's too hard to distinguish Sinatra, the S, and Sinatra, so I just used Sinatra as the name. But I realized later that X is 10 in Roman numerals, so it might be 10 times only faster. But let's just ignore that. Is it really 100 times fast? Well, it depends on the definition of fast. The routing and handling logic is 100 times fast, which means that whole world apps are 100 times fast. Of course, the framework handling isn't the most expensive part in web frameworks. Obviously, the app itself has the most weight. But even in real-world benchmarks, making routing 100 times fast can lead to a 2% gain. So I'd say it's like a free lunch. You can just change the base class and get a 2% performance gain. Now, how did I make it 100 times faster? That's the main part. And I'm going to introduce a technique called benchmark-driven development and a toolset. So let's continue into the style. Benchmarking itself is a common technique used to measure the performance of a program. The Ruby world has many benchmarking libraries, including Benchmark, which comes as a standard library, and I'm showing Benchmark IPS, which is a gem in the slide. In this case, a program which adds up to 1 to 100 is benchmarked, revealing that it takes 2.5 microseconds to execute the code block. Given that, let's talk development driven by benchmarks. The concept of benchmark-driven development is simple. Before starting writing code, design a benchmark, then start writing code. Now make it fast, and the cycle continues on. This can be compared to TDD, which stands for test-driven development. In TDD, we start writing a failing test, then make it pass, then refactor. Do you see the similarity? The reason why I brought writing a benchmark first can be explained using this matrix. There are 4 sections in this matrix: broken and slow code, fast but broken code, working but slow code, and then finally working and fast code. We all know that making slow but working code to fast and working code is very difficult. It's easier to write fast code from the beginning. Now, when we start talking about bottlenecks, the first thing many people mention is that you should focus on the bottlenecks. If there's some significant bottleneck, you should work on that part. Or you should focus on the algorithm and make magnitude faster. Or you could just work on the entire architecture. Of course, that is perfectly valid advice, and you should stick to these principles. But that is not everything. In reality, there's not always something significant. There's not always something significant. No particular bottleneck could exist. For example, in this plane graph, a lot of blocks have the same length, so there's no particular significant bottleneck. Even if your code is working on a logarithmic algorithm, and it could still not meet performance needs. So, lots of slight slowdowns will impact performance as a whole. However, those are hard to find, since those are slight, even though they may be easy to fix. We should remember that not slow is not fast. In this example, we want to take any even number from the array numbers. The slow version always iterates through the entire array, while the fast version bails out early if it hits the first even number. This might not sound realistic, but we see a lot of this kind of code in real apps. They have the same time complexity, but the latter version is 10 times fast. To address this problem, while developing Xantra, I benchmarked really every single change. So in each pull request, I attached a benchmark, and I compared the before and after performance. Now, this sounds cool. You could run benchmarks as much as possible to catch slow code, maybe on every pull request, just like I showed you, or on every commit, maybe. Even more, every time you type a row on your editor, you could run a benchmark. I have created tools and frameworks to keep benchmarking in the loop. Combined together, they will form a framework called BenchDD. So that's BenchDD. Now let me walk through how to do it. Benchmarking Xantra started from setting a measurable performance goal. So this means that defining what needs to be 100 times fast. So I wrote a benchmark first for that. My first benchmark looks very simple. It just takes an app and this is a rack app, so I called call and passed a almost empty hash. Now let's see the results. Xantra took 35,000 nanoseconds, which is, 35,000 nanoseconds per request. And I found another interesting benchmark target was Rhoda, which is known as a very fast web framework. Now, if I wanted to make a 100 times faster Xantra, this means that it has to complete one request in 350 nanoseconds. And now, the empty rack app I had just built takes 250 nanoseconds per request. This graph looks a little squashed, so let's make the axis log and make it easy to read. Comparing this, we see that we have an empty rect app, and if we want to make a Sinatra that completes requests in 350 nanoseconds, we only have headroom, 135 nanosecond headroom per request to do the heavy lifting and everything. We need to feed Sinatra features in 105 nanoseconds. That's what we found through benchmarks. So in code, it looks like this. The question is that how much time can we spend here? Now, setting the target was, well, it looks like 100 times is a fun target, but maybe a different target could be set. I initially wanted to overtake Hono, which is known as, which is a JavaScript web framework. It is known to be very fast. Now, the sad part is that full-featured Hono was faster than an empty rack app, so Hono could complete requests in 51 nanoseconds. And I wanted to overtake, but it turns out it was kind of impossible to do that in rack, so I just dropped that goal. Sometimes benchmarking is useful to set a goal itself. Anyways, we now know our goal. We now know our goal. So now it's time to write real code. So the process goes like start Vim, write code, run a benchmark, start Vim again, and then benchmark. So I started writing code like this. I started from writing routing code. Do routing takes an env, and it checks. I'll talk about this later. But the problem I found that is not fun at all, because look at the timestamps. I was running benchmarks, 10 benchmarks in like 5 minutes time, editing code. And this is obviously, well, it was kind of fun, but not really the ideal process. So to remedy this, I created a benchmarking framework. Now, this is a kind of a way to describe benchmarks. This is a DSL-like RSpec. It has a setup part, a dataset part, and a scenario part. In this case, the setup part is not measured, and the scenario part is the part that is benchmarked. So yeah, I have created a benchmarking framework. Sorry, I flipped the slides. We see that designing the workload is very important. Workloads should be realistic and representative and compact at the same time. For Sinatra, I prepared multiple tiers of workloads. The small one is a randomly generated set of requests, which consists of 10K, so 10,000 requests. The large one is a log collected from a real Sinatra app, which consists from 100,000 requests. We use the small one when running benchmarks in a tiny, small loop. So when you're writing code and trying to experiment, we can use the small dataset to get results fast. And to get more accurate results, we use the large one. Another problem is that benchmarking does not provide us enough information. What benchmarking tells us is the time per iteration of the current code. But however, what we really needed is how did the performance change before to after, and why did the performance change? So in this case, the only information we know that is the time per iteration. This is where profiling comes in. Explaining performance is exactly what profilers do. So as I maintain my own profiler, I've added a new view to show performance diff between two revisions. This is called a differential flame graph. Unlike a normal flame graph, the colors some frames are colored in red and blue. The red ones indicate that, so this flame graph is generated from 2 benchmark results and 2 profiles. The blue flames are the ones that get improved performance from the previous benchmark, and the red ones are the ones that got degraded from the last one. So seeing this, we can see that the blue ones got better and the red ones got worse. This gives us hints to optimize. Actually, this screenshot is not from my profiler, but this is actually a screenshot from Brendan Gregg Sensei's site, and there is a reason. Because his book is in the bookstore. Brendan Gregg is a great person. You really should buy his book. So in the bookstore, you should go now. And I have implemented another thing. This is editor integration. So I felt that reading FlameGraph is kind of tedious and not a thing that I want to do every single time. So I have made a editor integration that shows the time spent per line in ghost text. Do you notice the code text in gray? For example, the continuation check on line 22 is spending 82,000 nanoseconds per iteration, indicating that this is a possible hotspot. This is implemented in cooperation with the benchmark framework and PS2. When a scenario runs, it automatically engages PS2 profiling. The results are recorded in some temporary directory, and the diff engine in PS2 generates the differential flame graph and data for the editor integration. So now we have walked through a single cycle of BenchDD. It is important to write a benchmark for each feature, not each tree only. In the case of Sinatra, I wrote benchmarks for routing, handling, actions, and more. Now we'll see how I improved performance for each feature in detail. So making Sinatra 100 times faster. So this is a reminder. We need to fit all features in 155 nanoseconds time. We have to start from optimizing the significant. Routing is the largest part in Sinatra, web frameworks in general, which is the equivalent of what Rails.rb does in Rails. Some algorithms come to mind, like trie-based routing or linear routing. There are multiple options of algorithms for routing. One is linear, so it tries to match every single registered route for request. And another one is a trie based on a hash, data structure called a trie. Now, the one is ON, and another one is logN. So there's a trade-off. It's important to know where the line where a simple linear algorithm moves to a complex log algorithm. For 10 to 20 routes, linear routing was faster, which was found by benchmarking. So for Sinatra, it automatically switches the algorithm based on the number of routes registered. Now that we have implemented routing, we have 84. It turns out that routing consumed about 50 nanoseconds, so we have 84 nanoseconds headroom to go. We have many more features that we have to implement to make Sinatra a useful web framework. Not only routing makes a framework. We need to implement param-syntaxes, before and after actions, and cookies. And those may not be bottlenecks, but they're still challenging to fit in 84 nanoseconds for a request. Sinatra has a params API. If you call params in a handler, you can get the params passed to a request. The problem is that params is a method call. and method calls are actually expensive. If we could make parent an instance variable, that will make a gain. However, that is an API change. Obviously, add params an instance variable is faster, but it's obviously mutable and can do less work. Sinatra supports both. So users can gradually switch to the instance variable version and gain performance. So there is a lesson learned here. Performance can influence API design. If you start from params and make that a public API, you can't change it easily without introducing a breaking change. You have to carefully check every option. Another example is the request object. Request is another known, it returns a request object. It's kind of useful. Now, can we change this to gain some performance? We have some option to implement request, but actually, there is another usage. So unlike params, you can call request.env or request.params to get another object. There's multiple options to implement this. Option 1 is making it a class. Option 2 is making it a data. Option 3 is making it a struct. The data is the fastest of the three. It's all params. Sorry about that. So the obvious winner here is data. One interesting thing is that these results get reversed when widget is off. When widget is off, class is actually the fastest. So a lesson learned here is that it is important to experiment in an environment near production. Another feature is before and after action. Before and after actions can be registered, and those are saved on the app startup. Those get called on every request. So they can be used for authentication and other checks. There are in Ruby, there are a handful of ways to call a proc. One is block call, so you can just call .call on the proc. And another one is instance exec, and another one is instance eval. These have very different performances. Proc call is the fastest, but in this case, it was unusable since the execution context changes. So the options left are instance exec and instance eval, but benchmarking found out that instance eval was somewhat faster. So I used instance eval here. However, 422 nanoseconds is already 95 times faster than Sinatra, so we're breaking the 100 times line. So we have to come with another strategy. One way is to just make the before action actual method. We just call define method. Instead of saving a proc, I just defined the actual method and called it later using send. Calling methods is faster than calling blocks and allows logic. So this gained us significant nanoseconds. However, send is kind of still slow. What if we could just call a static method? We could do that, but multiple befores cannot be defined in this version, so it's kind of breaking. However, this led us to jumping 145 times fast Sinatra. Now, one last feature I'd like to introduce is rack session. This is technically not a part of Sinatra, but many Sinatra apps use this. So session handling wasn't in the original benchmark, so I'm not showing numbers here. But profiling shows that rack session usually consumes quite a lot of CPU. I tried to implement an equivalent in Rust, and it was quite fast. So just for information, and more, I reduced hash access, reduced object calculation. In this case, hash check the flow pattern, you see a lot of this flow pattern in Ruby code, but it actually exits hash key twice, so that's some damage caused to performance and reducing a lot of things. So wrapping up, building Sinatra was removing a ton of small debris. Doing high performance was not making it fast, but not making it slow, because 10% slower code is 150% slower code. Now I'd like to introduce some tips for better benchmarking. Does this presentation matter to me? Yes, because in Ruby and Rails, CPU time is very precious. Many people say that the database is the bottleneck and Ruby code won't matter, but actually Rails isn't that I/O bound. It only does I/O-bound I/O for like 50 to 60% of the time. And reducing 1 millisecond in Ruby code could go very far, especially when you scale. Another important thing is to not do gacha. Gacha machines is, by the way, the photo on the left, right. You can pay 100 or 200 yen to get some random mikyang goods. And well, doing benchmark, like repeating benchmark commands until you get a good result is tempting and fun, but that's kind of wasting time. If you are unsure, you should do a statistical hypothesis test. And Wajit? Enabling Wajit during benchmark is important. Just as I said, keeping the benchmarking environment close to production is important. Wajit engages jitting for methods called 3x, so a short warm-up should suffice. When profiling affect benchmarking, that is a yes. You will see lower scores with the profiler enabled. But that's OK, as long as the overhead is consistent. And one last thing, benchmarking CI. So the continuous benchmarking idea is kind of sounds like a thing to do in CI. Why do it in local when we have like GitHub Actions or something? Well, that is because CI environments are very unstable. You don't get the same results from the same code. They have an unstable-based CPU. You might have some noisy neighbors. The libraries could get automatically updated, and hyperthreading could be enabled or disabled. So wrapping up, do you now feel benchmarking? Some optimizations I covered today won't be easy to do after writing code, but when the instant you're writing code, that is possible. So always run benchmarks when writing code, and find them before you git commit. So thank you.